Hey, Computer Science 120A. I'm going to show you how to use Makefiles. So far in all of our labs, we've worked with source code files and the compiler directly. So here, for instance, I've got a file open, hello.cc. That's over here on the right. And you can see that it's over here in my file system. And if I want to compile it, I would type out Clang++ and the name of the file and would think for a second, and out comes a binary program, a.out, and to run it, I would do /a.out. Now this is a perfectly good way of doing things. The gotcha is that as programs get more complicated, or as you want to configure how you build your program, remembering all the different commands to get things to be built can get quite complicated. So we've got a variety of different tools out there to help us build our software. These tools are like, well, we're going to use Make, but there's other things like Xcode, Visual Studio, not Visual Studio Code, but Visual Studio from Microsoft. C-Line is another product from another company. But there's a variety of products that allow, or I should say tools that allow software developers, programmers, to write their source code. And then instead of remembering the exact command to type in or to input or whatever, instead we can distill that information into a file and then keep those recipes in that file so that we just don't have to retype these commands over and over again. What I've got here is a project from last semester. And in this project, this is going to be similar to your Lab 3. It's got two parts in it. Part 1 and part 2, but now it has this file here called Makefile, and as well in part 1 and in part 2 there's also a Makefile. Now there's a page on Canvas that describes Makefiles in greater detail, but I want you to know that all of our Makefiles will have the same targets, and that information is always at the root level of your README, reminding you how to use that Makefile. Let me I've already got this repository cloned onto my computer, and it's right here. So I can go into that directory, and I can see that there's a Makefile already right there. That's the same Makefile that's right here. Now you can open up the Makefile if you want. And by the way, I'm using a Macintosh, and everything that I do here will work 100% the same on your Linux system. I'm using this Mac because I've got the video capture software on it. It makes my life a lot easier to just do everything from this Mac. Now, anytime that you see me type SUBL, I'm just opening it up in my text editor. You could change that command to code, and it will open it up in your text editor. I just want to show you what this file looks like. And this file uses a different language to describe how to build stuff. You don't need to worry about how this is done. It's just another file. Don't need to edit it. Don't need to make any changes. All your projects will always be provided from Lab 3 onwards with a Makefile. If I go into part 1 and we try to do this lab, for instance, I open up this source code file and I read the README very carefully. Let's pull it up in our web browser. It gives us a whole bunch of stuff to do here, numbers 1 through 12. We're going to be writing a program that calculates the basal metabolic rate. And it gives us these two formulas right there. One for men, another one for women. We're going to change the code, and instead of me compiling this program directly with Clang++, I'm going to use Make to do it. So I'll do this really quickly. And I won't do it for all of the things. I'll just try to follow along with the to-dos. Let me make this window a little wider. There we go. So let's declare a double variable to store the weight. And I'll label this as done. That's the advice that I've been giving you guys. So that way you remember what you've changed. Oh, and I should always initialize this to some known value. Here I can initialize it to 0.0, whatever number. I'll give it a function number just so I know that if I see a weight of 42, it doesn't make sense. And let me make this window a little wider. Standard cout to print the prompt. And we want these to be exact. So please try to make sure that whatever we ask you to print out, you do the same exact message. This makes sure that when we run our tool, use our tools to grade your homework, that we're going to be able to make sure that what you wrote matches what we expect. And then we're going to collect from the keyboard the input. We're going to read this into our weight variable. And what I'll do is I'll change those to done. Now I've made changes to 3 lines, and I always recommend every time you make a small change, compile. Every time you make a small change, compile. So if I came over here, I'd have to type clang ++ bmr.cc, and that would work. But because I have this Makefile here, all I need to do is type make. And the Makefile will have stored, because I and your other instructors will have written into the Makefile the recipe needed to build this program. And instead of having an a.out that comes out, a.out is the default name, it's going to generate BMR. Now, how do I know this? Well, this is because it's described in the README. It will tell you that it's going to generate a command called BMR. That recipe in the Makefile says when it builds bmr.cc to output the program as BMR. Now, other things that this Makefile can do are other targets, such as, and if I go back to the root level README, it has make all, which builds the project, make clean, which removes the object and dependency files, make spotless, which is like, it's like clean, but even more clean. And then it's got a couple other targets like format, lint, and authors to help you figure out if you've got all the parts put together right. So format is going to show you whether or not the formatting of your source code is correct. The lint is going to check to make sure that you don't have any jagged edges in your code that could catch and create some lint. And test, finally, and authors will check to make sure your authors file is correctly formatted. And then test will run some automated tests. It's not an auto grader, but it'll give you some idea of how well your project's going to do overall. So let me I'll make it spotless. And you can see it will delete all the stuff and put it back to the way it was a second ago. Now, it doesn't change your source code. It doesn't change the source code. It just deletes the files that are generated by the compiler. So let me do that one more time. I'll hit make, type ls, and you can see the compiler generates bmr.o. That's an object file that contains intermediate code for the compiler to make the binary. bmr.d, which is a text file which tells the compiler what are the dependencies for what we're building. bmr.cc, that's the file that we started with. And bmr with this little asterisk next to it. And that asterisk is actually not part of the file's name. I just have it set up in my shell to put a star next to things that are executable so that I know what commands I can run. And if I run the program, well, right now it does this, as I expect. I'll enter 12, and it ends. So these 3 lines I added look pretty good. Let's continue on with the program. Declare double to store the height. I'll put a crazy height number in there. And then we want to use cout to print a prompt. Again, make sure it's the same. Spelling matters, spacing matters, all of it matters. So make sure it's exactly the same as what we expect. And then finally use cin to capture the value and store it in our variable height. Let's indent that nicely. Let's compile. And here's nice, I just type make, and it's going to recompile it. Now, if I type make twice, it will do nothing because I've not made any changes. As long as I don't make any changes, it will not recompile. But the moment I change something, add a comment, whatever, it's changed that file, and now when I type make says, aha, that file has changed. I need to recompile, and we'll recompile the file. So let us mark those as done. Now we need an int variable for our age. Let's initialize that to something silly. standard out for our prompt. And standard C in, oops, wrong direction, for the variable to store that into age. Now again, made some changes, type make, hey, it compiles. Now, might be a good time to check our progress here. What's our weight in pound? We weigh 150 pounds. What's our height in inches? Well, we're 5 feet 10 inches, so that's 5 times 12, that's 60, plus 10, that's 70 inches. And our age in years, well, we're 65 years old. Okay, well, it does exactly what we expected because it did this block right there, lines 26 through 30. Did this block right here, 33 through 37, and it did the block 40 through 44. So we're making good progress. I made a change to the file. Now I'm using the keyboard shortcut Control S to save. I recommend that you learn all sorts of keyboard shortcuts so it saves you some time. Oops, I want to recompile. Again, if I make no changes, it's not going to recompile. And here, let's do a double variable to hold. What do we want to hold? Double variable to hold the man's BMR. Initialize this variable calling it BMR. So, man BMR, and we'll initialize this to BMR man. Oh, it's a function call. So let's look at what this function is. Okay, so this is the function that takes a weight, a height, and an age. Now we've got those values right down here, so I'm going to call BMR man and call it, use weight, because this variable maps on to this one right there. The next one is height, and the last one is age. And well, right now, this compiles, it just returns 0 all the time. So it's just going to return 0, and it's technically not a double, but we'll make it a double, make it look nice, make this one look nice too. Come back over here, compile it. Oh, what's going on here? Unused variable. Oh, that's okay. I'm not using this variable. It's normal, but the compiler is saying, hey, you declared a variable, you initialized it to something, and you should use it, but you're not, so, oh well. Now let's do the same thing with the woman. And I'll initialize that BMR woman function above. Again, weight. Well, let's just double check. If I scroll up there, it should be the same. It should be weight, height, age. Okay, great. Now remember, this weight that's in main is different than the weight over there that's passed in. It's copying the value in. It's not magically being transferred. And now I'm not going to say that these two are done because I still have to write these functions. But I'll just continue on doing this part here because it compiles, I think. Let's check. See, it's really convenient having that make. You don't have to type out Clang++ all over again. And I'm using the arrow keys here. If I push the up arrow, it goes to the last command that I typed. And that's a time saver. And then we're going to do the last part, standard cout. Print that out. Well, BMR has replaced the constancy variable in man's BMR included. Okay, So we should actually format like this. So this ought to be a man's BMR, so that's our variable right there. Put a new line at the end of output. And we're going to do the same thing with women. And we're going to replace the BMR, the capital BMR here with that variable, woman BMR. And add a new line at the end. Now, we should have it, like, I think this is going to compile. Let's check it out. And it does compile. Now, we should imagine, like before we run it, we should imagine what it's going to do. So it's going to ask us for the weight in pounds. We're going to put that value here. It's going to ask us for the height in inches. It's going to put that value there. Ask our age in years, and it's going to put that value there. And then it's going to call these two functions, which right now do absolutely nothing. They compile, but they do absolutely nothing. And they return 0.0. So man BMR will be 0.0, and woman BMR will be 0.0. And I'll see it print man colon 0.0 calories per day and woman colon 0.0 calories per day. Let's see if my guess is right. So again, check to make sure it's compiled. Oh, I've made a change, so it compiled it. Run the program. Enter weight in pounds of 5 pounds. My height in inches, 23 inches. My age, 45. Okay, it did exactly what I expected. It returned 0, and it printed out 0 calories per day and 0 calories per day. Now, just to make sure we understand this, I'm going to change the BMR man to, I don't know, 123.456. And I'll change the woman to always return 567.890. Well, let's just say 0.899. I'm going to save this, compile the program, and now what I expect to see is I expect to see over here 123.456, and what I expect to see over here is 567.899. Let's see if that happens. Doesn't matter what numbers I put here, and it works. Okay, so now our instructions are to use the Mifflin-St. Jeor equation for men. If we look at our README for part 1 here, the instructions are there. It's going to give us a formula, and that formula is this. And all we need to do is transcribe this formula into our program so it can calculate it. So I'm just going to copy this right here and put it here as a comment to myself. Oh, that doesn't look nice. I guess I'm gonna have to type it out. 4.536 times weight plus 15.88 times height and minus 5 times the age, 5 times plus 5. Okay, let's translate this into C++ code. So I want to return 4.536 times weight. It's a good idea to wrap these in parentheses to make sure that these get execute in the order that you expect. Remember, we follow the rules of PEMDAS, but sometimes we can get ourselves confused. So why not just wrap everything in parentheses? I'll wrap the whole thing in parentheses. Now, you might be saying, like, why don't I declare a variable and assign it to it? I could. The type here is double, and I could initialize it, like so, and then return BMR. But there's really no point in storing it and then returning it. So that's why I was just thinking, oh, I'll just return this value, because it's just going to calculate it out to be some number. Now let's see if I compile it. Hey, no error so far. Run it. Now I could enter in crazy numbers, but I've got some data right here that I can use. I'll use Kobe Bryant. So Kobe Bryant is 212 pounds. His height in inches is 78. His age is 41. And the BMR calories is 2000.27. And we see we get 2000.27. That's a good sign that we're on the right track. Now, the woman's calorie, BMR is wrong. So we should change that. So the equation there is it's essentially the same thing except the minus 161. So what I can do, I can copy this, put it here, and instead of saying plus 5, I'll say minus 161. And I'll compile, see if I made any typos. No, great. I'll run my program. This time I'll use Simone Biles. She is 104 pounds, 56 inches, and 26 years old. And I have 1070.02. And that matches what I expect here. So I can come down here, pat myself on the back, replace those with dones, because this all looks like it works. Now, I've tested this by hand. Lucky for us, our Makefile also has a test target. If I type make test, it's going to run a battery of tests to see if, more or less your program's okay. Now, the first thing it tells me is my authors file is malformed. So if I type make authors, it can give me some idea of what's wrong with my authors file. I didn't even do it. So let's edit that. In the author files, all you need to type is your name, your email address, and your GitHub username, and then also your partners. My partner here is Peter and Peter. Peter at cpsc.edu, and their GitHub is Peter and let's check that. Oh, great. Okay, so now our authors file is well formed. It tells us this information that we have put in there shows up. If I do make test again, it's telling me my formatting is okay. There's some linting problems, and it does some tests, and it passes the test. Now, it's only useful to run make test if it compiles and you've tested it yourself. If you don't have it compile and you don't test it yourself, then these tests are meaningless. Remember, garbage in, garbage out. And tests aren't there to make sure things work. Tests are just testing to see if what we expect works as we expect. And if you do something really, really crazy or something that we don't expect, you can actually get false positives or false negatives. So always make sure you test all this stuff. Now the other two targets are make format. And format will just check your formatting. So if I look at this file right now, I've followed all the Google C++ style rules to make sure everything is formatted correctly. I did forget to change this to do. Should put something here, describes this program. Oops. Using the Flynn. That's descriptive. Change that to done. But do make format. Oh, what happened here? So this is a very common problem. You look at this. So the way to read this output is it's telling you that this is what you wrote on lines 1 through 4, and this is what it should look like. And the lines here are 1 through 4. Now, you look at this very carefully, and you squint your eyes, and you say, they look about the same. The difference is right here versus right here. Notice how when I highlight this, there's a space there, and when I highlight this, there's no space there. This is very common. Right here, there is a trailing space. And the Google C++ style says you cannot have trailing spaces. So you sometimes get these outcomes where this looks the same as that, but really it's different because this one has a trailing white space and this one does not. So if I erase that trailing white space, save this, type make format, it looks good. Make lint as a separate target, it will run a linter and it'll give you some idea about what's wrong with your code. Now, the linter here is saying, hey, you have a to-do, You're not allowed to have to-dos there unless it's owned by somebody, so you could change it to be owned by you. Or if you're finished with it, change it to done. So it's highlighting on line 12. If I go and find line 12 right there, I left it to do. So to-dos, according to the Google C++ style, just can't be left there on their own. You either have to have them owned by somebody, so you can label this person is going to do it, or as I've suggested, because we're doing this for 120, we don't need to label it to do for somebody. If you finish it, you can just say done. And that way in the future, if you find a mistake, that you're confused, or you can't remember what was done or what wasn't done, you can always remember that all the places that say done was a to-do that you fixed, and now you think you're done with it. This is going to be another place where it's going to complain. And I would correct that to a done. Oh, and we forgot one last one on line 60. So the way I read this, I look there, warning, it's in the file bmr.cc on line 60. Ah, there it is. Done. So I've saved the file, run make lint. Let's see what happens. Oh, hey, that looks good. So I'll do a make spotless to get rid of everything. Now that again doesn't get rid of your source code. All your files are still there. Just gets rid of all the stuff that was made. I can now run make test. Get a green check mark for formatting. Green check mark for linting. It builds my project. It runs some tests. Tells me that my tests have passed, and it tells me that it knows who I am because the author's file is well formed. This whole Makefile is just a time saver because I or you or anyone can put recipes into that Makefile, and then the make command can use those recipes to do actions for us. So make will build, make clean will delete some stuff, make spotless cleans everything up, make format is going to check our formatting, make lint, I'm not going to run it because it takes a while for it to execute, make lint will check for lint in our project. Make test will do a battery of tests to make sure that your project is ready to be sent back to us. Now, if I was doing this on my own or the partner for a lab, I would have made lots of small commits along the way so you can backtrack in case you make a boo-boo. But I hope that gives you an initial idea of how to use a Makefile. I've got also another project here. This will be probably similar to our lab 4 when you get to it. And in this one, again, let me show you. Let me get this window out of the way. This one also is organized the same way. It's got a Makefile at the root level. It's got 2 parts. And in part 1, we've got a Makefile with a recipe, but now our program is spread across multiple files. This is our main file, units.cc. Our program that we're building here is called units. And this information is all listed over here, which explains to you how it's done, and it tells you how to run the program. But the Makefile has a recipe to build it. This one, units.cc, will be our main file. Unitsfunctions.cc and unitsfunctions.h, this is where we're going to put all our functions. So we're going to make a couple different functions and then use those functions in units.cc. And then I provide you unittest.cc. In future projects, if we're going to put functions in a separate file, we might have another file called unittest, and that's going to have tests just for the functions. So we're going to have one set of tests for the entire application. That's what I did a second ago with BMR. And then we're going to have a separate set of tests for units. Let me switch over to that directory and we can take a look at that. Again, we have a Makefile at the root level. We've got 2 parts. I'm going to look at part 1. I'm going to look at part 1, which is what we were looking at in the web browser a second ago. Here we've got a Makefile for this folder. We've got units.cc, which will be our main, unitsfunctions.h, and unitsfunctions.cc, which will define our functions. And then we have a separate file called units_unittest.cc. You do not need to edit that file. You do not need to edit the Makefile. The only files we'll need to edit is this one, and this one. So units.cc, unitsfunctions.h, and unitsfunctions.cc. Let's open up those files in our text editor. So here's units.cc. You can see it's a main file. It has a main function. And at the top of it, we see we've got a pound include for IOStream. And now we have a new type of pound include, where this pound include uses quotation marks instead of angle brackets. And it's using the name of the file that we have in our project right here, unitsfunctions.h. Let's open up unitsfunctions.h. In this project, we do not need to change this file. And we know that because somebody's written at the top, do not edit below this line. So this file is perfect the way it is. And what it has here is 1, 2, 3, 4 function prototypes. Each one of these prototypes tell us about a different function, and the name implies what it does. This one's called milliliters to teaspoons. This one's milliliters to tablespoons. This one's milliliters to ounces. And this is milliliters to cups. And each one of the functions here takes a double as a parameter, a single double as a parameter, and then returns a double. Our job in this project is to write the bodies for these functions. Now, you might say, oh, why don't we just start writing them here? But that's not what we want to do. What we want to do is we want to leave this unchanged. And we're going to open up unitsfunctions.cc. In this file, we actually have the full function definition. So let me go through this one more time. In units.cc, we have our main function. This is where we're going to use the functions. In order for us to use the functions, we're going to pound include the prototypes, meaning we're going to copy and paste the prototypes from unitsfunctions.h. Unitsfunctions.h has the function prototypes that we're going to use in our main, not the definition. In unitsfunctions.cc, we've got the 4 functions that we're going to define right here. The files that will get compiled are units.cc and unitsfunctions.cc. The units functions h does not get compiled directly. Now you can see why a Makefile is really handy here, because now we're working with 3 different files, not just with one file. And with a Makefile with a recipe written inside of it, we don't need to remember the complicated commands or the long commands that might be used to compile 3 different files together into one program. Instead, we would just type make, and the Makefile knows how to combine everything together into one program. Now, when it builds it, it does give you a warning that these functions that we're looking at right here on line 5, 13, 23, and 33, they don't return anything, and we're expecting to return something. Notice it says return a double right there, and it does not have a double. So let's define these functions just so we can get an idea of how this works. So this one converts milliliters to teaspoons. So if we divide our milliliters by 4929, it will convert milliliters to teaspoons. So we'll return, this is the volume in milliliters, volume divided by 4.929. If I make, compiles, that's good, but it still has those warnings. But I'd like to know if that function's correct or not. And this is where unit tests come into the picture. I have written tests for each one of these functions that you can use to verify that you've got the right math. So if you type make unit test, on your Linux system, it will not have all that garbage there, and it will run correctly. For some reason, this has failed, which is unfortunate. I did not test this ahead of time. I just assumed it would work. But I can hop over to my Linux computer and go to the same folder that we have here. And I can show you that if I click make unit test, it's going to compile it, and we can scroll up and look at the output here. That's a lot of outputs, so just gotta be patient. Scroll up carefully. And, okay, here's where I typed make unit test. And it gave me some warnings because out of the 4 functions, only one of them returns. So it gives me 3 warnings that I have the other 3 functions not returning anything. And it tells me that it's running 8 tests from 4 suites. The first test is the teaspoon test. Well, I just wrote the function here, milliliter to teaspoon, and so it's telling me that it ran these tests and it passed. The next test is the tablespoon test. Now, I have not changed the tablespoon test, and what it's telling me is that it did not pass. It's showing me that it tried to calculate milliliters to tablespoon, and it got garbage. And so it's telling me that that test failed. It ran a whole bunch of tests for milliliter tablespoon, and now it's telling me it failed. And the same thing is true for milliliters to ounces, and the same thing is true for milliliters to cups. Now, if I write the tests out correctly, if I write the code, I'll be able to run the unit test to verify that each one works correctly. Let's try it. So to convert milliliters, so this is milliliters to tablespoons, but if I read the notes here, it says first convert the milliliters to teaspoons first. Then, I'll move this over so we can see the whole thing. First convert the milliliters to teaspoons first. Then you can divide the teaspoons by 3 to find the number of tablespoons. So if I first take volume and convert it to teaspoons, I can then use, take that and divide by 3.0 because it's doubles, and I'll have the right answer. Let's see. Okay. So it passed some tests. Let's scroll up and see what tests it passed. Okay. So teaspoon test, that was this one. That one passed. Tablespoon test, that one passed. But the other ones didn't pass. So why don't we come down to milliliters to ounces? And we can see that it tells us exactly how to do it right there. So what we got to do is we got to convert, it's cutting it off. There we go. So use milliliters tablespoon function to convert volume to tablespoons, then convert tablespoons to fluid ounces. Okay, so if I take the volume and convert it to tablespoons, so I'll go milliliters to tablespoons on volume, and then convert tablespoons to fluid ounces. Well, I can divide the tablespoons by 2 to find the number of ounces. Make unit test. Okay, we're making progress here. If I scroll up, you'll see that now I'm passing the test for teaspoons, tablespoons, and ounces. And now we have 1 test left, or actually 2 tests left. So this one, we read the instructions. If we first convert to ounces, then we can divide by 8 to find the number of cups. So I'll convert the volume, milliliters to ounces, volume, and then divide by 8. Well, I gotta return it. Hey, now everything passes. Now, let me show you, now that you've got an idea of like all this is working, what would happen if I did the math wrong? Let's imagine that I didn't divide by 2, instead I accidentally did this wrong and I divide by 1.25. I'm slightly off. And this is for milliliters to ounces. If I run unit test, if I make unit test, it's going to show me that a whole bunch of different tests failed, because remember, I'm using this function here over here. So not only does this function break, but also breaks this one. There's a chain reaction. So I'm going to scroll up. And it's going to show me units ounce test. And it's going to tell me that it tried to do milliliters to ounces on -5. And it tried to calculate it. It got that value. And it's outside the range of expectations. Because we're using decimal numbers, it's not going to be precise. It's checking to see if you're correct within 3 decimal places. But we're way off because we're dividing by 1.25. If we look at this output very carefully, we can try to figure out what's going on. But a very important thing to do is to say, how can I verify? If I've got a certain number of milliliters, how can I convert them to ounces? And this is where you can use your favorite search engine. You can use an app on your phone to convert from milliliters to ounces. So that way you can look at the value and say, like, why am I getting this value wrong? Where am I going wrong with this math? And so if I correct this back to what it should be, which is 3.0, compile it, it passes. Now, again, it's not supposed to be mysterious. You need to have a clear idea in your head of how the math works and how you can do this math on paper in order to write this stuff out. Otherwise, it's just kind of magical and it's really hard to decipher. Anyhow, the Makefile targets help us just be more productive so that we don't have to type out long, complicated commands to run our unit test, to run the linter, to run the formatter. We can just type make and then the target, and it will just do it for us. And again, you never have to worry about how to make a Makefile. The Makefiles will always be given to you in 120A and also in 121 and 131. It's a common technology that we use throughout the 3-course progression. If you learn how to use Makefiles, you can apply that knowledge to any other type of build system, because Make is the great-great-grandfather of them all. I hope this gives you a good brief introduction to how to use our Makefiles for 120A's labs. And if you go on and use Makefiles in other projects, you'll find that their targets will be very similar to ours, but not necessarily identical. And sometimes you'll have to look inside the Makefile to see what the targets are. And you can always ask the person who wrote the Makefile how it works. Great. Thanks for watching the video. Don't forget to like and subscribe.